السلام عليكم. بسم الله الرحمن الرحيم. This will be the course sessions. We'll direct quickly. There's something named coefficient of expansion. Coefficient of expansion, it is just get like this. Okay. So the coefficient of expansion is beta, which is the rate of change of the density in respect to change of the temperature, which is equal 1 over rho, which is the density what we need, and this is a coefficient, by the way. So in another term, that is rho equal 1 over beta with minus sign dv by dt. It is partial, of course, because it can change with other parameters like Caba, which is or K, which is due to the pressure itself. Okay, this is rho, by the way. So let's continue. The ideal is an example: B equal RT. So rho equal B equal rho RT, which is BV equal MRT. So just rho here. So rho equal this one, and we know that d rho by dt, we just make a derivative. So make a derivative for respect to t. So t minus 1 become t minus 2 with minus the power down minus 1, the derivative, normal derivative. So beta equal 1 minus this term and this term, which is, you will find it, this term is the inverse of this term, so it is 1 over t. Okay, so it's just an example. For coefficient of compressibility, it is rho dv by d rho. The general term is the change in density is equal to the density multiplied by the first coefficient multiplied by delta t, and the second coefficient inverse multiplied by the delta b. Okay, it is very simple, just not delta. So we name it as sorry, delta rho, not del rho. Del, it is partial, but we, for approximation, for small approximation, so it is del rho will go here, k will come here. It is very simple. Del rho is here, this is rho, so rho will go here, beta will go here, so del rho, if you go, so it will be inverse like this. Okay. Regarding viscosity, it is defined as multiplying the viscosity to the gradient of the velocity from the boundary layer. It is the shear stress. The shear stress force, it is what we have as an area as in depth multiplied by the shear stress, so we will come having the viscous force. An example, if we have an inclined surface with theta, so there's W, put the W in, because this is in theta direction, so put W in theta direction, it will be sine. In x, sigma x should be equal to 0. So, and this is the shear force as we discussed it before here. It's very simple. Now we know that this velocity here, we assume, of course, this gap is equal or less than the boundary layer. Later on, we're going to discuss about what boundary layers and why these approximations can be valid and when it will be not be valid. But for simplicity, if this gap is less than the boundary layer, which is mean we are still here, the boundary layer, which is from here to here. The remaining one, it is V or U is equal constant, but from here to here it is varies from 0 to till U. So if we assume it like this, it is equal to the boundary layer. So we know that is by anyhow equal or less, we know that is the layer here equal to the velocity of the block, which is U, and the velocity here is equal 0 because no slip condition for the oil or whatever. So delta U for approximation it is U minus 0, and delta Y is H. Put the numbers, plug the numbers, you'll get the velocity. Here is just a simple mathematical you need to know. There is something named kinematic viscosity. It is mu divided by rho. We're going to use it later on, why we need to use kinematic viscosity later on in the dimensionless analysis. The surface tension, it is very simple. It is a force per unit length. In case of plane, it is plane which has been full plane. It is 2b and the surface tension. If it is droplet, it is delta b, the equal to 2 surface tension divided by r. Imagine that the surface tension is like a rubber. So when you have a rubber or something like this, so if you have a rubber, 1 second. So imagine if you have a droplet. So imagine that this surface is a rubber, which is exerting a pressure force in this direction. A pressure force in this direction. Okay, that is why we put it as delta B. Okay, and in case if we have a soup bubble, why this one is twice of this one? Because in the soup bubble also you have force going in this direction from inside. So we have two surfaces, okay? Now let's go. Okay, a simple example. This is very straightforward example. If we have a tube, a capillary tube or something with very small area, so the water rise here, as we know, like in the trees, etc. It's the same concept, and the rise here h. This rise h, we need to know it. It is very simple. We know that it is force equal this equation by anyhow. Also, we know that is a delta B, the pressure which is going to exert on this surface due to the tension, it is going to follow this equation. So, based on that, we can understand even that, of course, delta B is equal force divided by area. It is the same concept. So, if we put delta B, which is equal to this one, what is the area? Area, it is this area. This area, okay? It is very simple. So, just plug the number. It is very simple. This is the pressure. So let's do it like this because we don't need to lose a lot of time. So this part is the pressure, and this part is the area. So force equal area multiplied by the pressure. So R, of course, R square is here. Huh? So it is not by square, it is R square is here. So it is R square here. So plug the numbers r by square by r square, so it will be r2 by r sigma. So this is the force, the surface tension force. Okay, so we need to know stress analysis, also force analysis, sigma y. So we know the force which is going to be parallel to this. We need to know what is this angle. Based on this angle, so like there is a sine, like this is a cosine. So cosine up equal cosine up fs equal to the weight of the water. Weight of the water is the surface. multiplied by the height becomes the volume, multiplied by density, multiplied by gravity. This is the weight of the water, weight of the column. So the height is equal to 2 sigma s cosine phi over rg. Phi, it is a constant for each fluid and walls. For example, if a glass with water, phi is equal something. Is this mercury with glass, phi is equal something else. Okay, that's it. Of course, I will correct this one. Okay, now the static bodies. It is very crucial to understand it. Okay, the static bodies, if we have an static body, big body, so we took a small slice of that body. The slice, it is 3D slice, which is, it is a dx, dy, and the dz. Okay, so uh, we need, when we are dealing with any pressures or etc., we need to deal with the center of that point. Okay, which is a body force. So when you do a stress force analysis, we need to make that forces coming to the center of the pressure. Yet we know that the pressure is going to, on this surface, there is another pressure going, whatever ever the pressure, we don't care now, which is just an assumption that there's a pressure here, pressure here, pressure here, pressure here, pressure here, pressure here. Somebody will tell me, okay, why are you not extending the pressure till it reaches this point? Because when you're going to extend it, it's going to have an effect of this one, and this one, and this one, and this one. So this pressure, we can assume, we can, let's say, assume there's a pressure here, but the interaction of all of these pressures to this point, no, we cannot know it, because I don't know how this one, maybe this one 10 pascal and this one 1 pascal. So the resultant here, it is, will not be unequal. Okay, so we cannot generate a general form if we're going to extend it. So what we need to do, the pressure first is not a vector. The pressure, there's another point, the pressure is a number. Okay, so we cannot deal with it as a vector. Okay, with the area it become a vector, with the area it become a vector. Okay, because it is representing the force with the area. So just for our information, so what we can do, we need to follow the truncated or the Taylor series. Taylor series is very simple. It is defined as, forget the truncated name, Taylor series itself. It is saying that if you have a point which is at y1, s, this is any function, and you have a function. If you need to get the other point, you need to know what is the rate of change of this curve multiplied by the distance here plus 1 over 2 factorial multiplied by the second derivative, or because the first derivative is the rate of change. The second derivative is the rate of change for the second time of the first derivative, which is the second derivative. Of course, it will be partial, because maybe y is changing due to other reasons, for x, for z, you get my point, for s. So the rate of change based on s, so we cannot put it dy, it is del y, because y can change for other parameters. So it is a general form, by the way. Multiply by ds, the distance squared, plus etc. 1 over factorial, 1 over 3 factorials for the third derivative, partial derivative, multiplied by del s power to 3, okay, and etc. This is Taylor series, but because we know already, we took already a small slice, which is dx, dy, dz, so we know, if you're going to apply it, that ds, which is the distance here, it is already small. If I going to take the square root of it, also the square of the d something, so it will be way, way small. So we can neglect this part. So we can state that any pressure or anything, any point, we need to refer it to another point. It is the same pressure here with the rate of change between here, multiply the distance. Distance here, it is, for example, dz by 2, or dz, sorry, over 2. So this is distance. That's why we said dz by 2 or dz divided by 2 squared. This is way small, so we can neglect it. So we can apply it for all. So any pressure, we can return it back to here. With respect of the Taylor series concept and the y and z direction, which is this is x, this is z, and this is y. So here is y is in positive, here x in positive, z in positive. Okay, this is, and Taylor series saying you have this point and you need to know the other point in the direction increasing, it is plus. And if we're going to turn back in the opposite direction of increasing or opposite direction of the axis, it will be minus. So y1, if we're going to use here y naught, it will be minus the rate of change multiplied by the ds. If we are y1 and we are trying to get y2, so it is in the direction of s, so it will be plus. Okay, so let's go. I will take the x one body force. We agreed it is only in the center. Let's close it. We know body force, it is in the center, the weight of the water or the weight of whatever this fluid. Okay, so it is rho v g, we know it, and we know v is dx dy dz. So Fy at the body force, which is at the center, we no need to shift it. It is rho dx dy dz g. In x direction, I will take it one by one. Okay, in x direction. In x direction, which is like this, we have this face and this face, which is mean we have the back face, this one, the back face, and the front face. Okay, if I'm going to check the front face, there is a pressure acting on the opposite direction, creating a force in opposite direction of x, so it is a minus force. So it is a minus force. Okay, what is this force? The force is equal to the area multiplied by b naught outside. Okay, there is a problem here. That is b naught. It is on the surface. It's not in the body, so we're going to shift it inside. Okay, so what we need is this one. Again, what we need is y2. So what we need is inside. From where we're referring it? From here. Okay, so we are going with, for what we need here, we are referring to this one. We are going to the x direction. Okay, with the increasing of x direction. Very simple. Okay, so we are here. We need to refer to this one. We are going with x direction. So b here is equal to b naught outside plus the rate of change, which is dB by dx, the rate of change dB by dx multiplied by the distance, which is dx over 2. Let's go. Yes, it is b naught. For first, it is totally with minus because it is in the opposite direction of x. So it's b naught plus d. Of course, it's not d del because the pressure changing in x and y and z. So there's a lot of parameters going to affect x. Del b by del x multiplied by dx over 2. So this one is truncated Taylor series multiplied by the area. Area is simple. dy by dz. Okay, dy by dz. In the other one is the same case, but this one with the direction of x, so it will be plus, so there will be force in plus, but we are need to refer from this center point to this one in opposite direction of x, so it will be b naught, this one, minus the rate of change multiplied by the distance, which is dx by 2 again. So it will be b naught minus, because we're going to, but the entire force in is a positive. Repeat the same in y, in z. It's very simple. Make sigma fx equal 0. Sigma fx equals 0. If you start to see it, there is no any fx except this one. So if you start this one with minus plus this one equals 0, you will find something really good, that this term and this term in minus, which is can be added together. This will be gone with this, so you will have, which is, let me see, B naught with minus, B naught with minus also. So you can add these two together, and this one will go with this one. So you'll have this formula, which is very simple, dx dy dz, which is equal to 0. So we can say that is del b by del x, or the partial change, or the partial derivative of pressure with respect to x is equal to 0. We can follow the same. Of course, minus is meaningless. Okay. Or the same in y, but the z direction, no, because we know it's not equal to 0. It is equal to Rho dx dy dz. So if we return here back, so in similarity to z, so del minus del b over del x, it will be over del z, dx dy dz, equal to Rho dx dy dz g. Why we use d not del? Because it is a dimension. It is not function of anything. So that means it's not partial derivative. There is no other parameters going to affect it. It is itself. Okay. So it will be dx dy dz will go by dxy dz. So you will have at the end is del b by del z equal to Rho g. What is this one? If you put del z, or why we change from del b to db and from del z? Because we know that the pressure is not changing in y direction. The pressure is not changing in x direction. So the pressure is changing only in z direction. So it is a derivative. It's not a partial derivative. So it is dB by dz equal Rho g. So delta pressure equal to Rho g delta z, which is h. And this is how we can prove the static head, which is Rho g h. Okay. Follow basics. I need to go very quick. This is regarding the hydraulic gradient. Hydraulic gradient, which is how much the, so here is hydraulic gradient, which is how much static pressure, which is can be generated without effect of the velocity. Okay, so this is the pressure here. So we know that is any point of pressure is equal to, from Bernoulli, pressure plus kinetic plus potential. Forget the potential if we are straight, so it is pressure plus kinetic. Because we are in straight pipe and does not change from here to here if we are inclined or whatever. So we assume it is, there's no change in potential. So it is pressure plus kinetic. So the pressure itself, it is Rho gh1, or the pressure itself, it is this one. And if we are making with beta tube like this, so it is taking the pressure and taking also the velocity effect. So the velocity will start here and will go higher. This will be a total energy line, energy gradient line, which is the full up, which is taking care of the pressure and the velocity, and this one will take only the pressure. So this one minus this one is equal to kinetic velocity, which is half Rho v square. Okay. The hydraulic gradient, yes, can increase. So if we have a bulb, so yes, then the velocity get increased, which is the pressure. So the velocity get decreased because increase in the section. So the pressure going to increase. When the pressure increase, the hydraulic gradient line get over. So this point can be higher than this point. In energy gradient line, it is impossible. Why? Because whatever you took from the pressure, it is going to velocity, and whatever you took from the velocity is going to the pressure. So either it will be constant, it is impossible due to the friction, so it will go down. Rigid body acceleration. Rigid body acceleration, it is the same concept what we are doing here. Why we using rigid body? So if we are using an static, fluid static, that means there is no any interaction between the fluid body or between the fluid body and the walls. In another terms, there is no viscosity effect. If in case of any viscosity effect, so the layers will take a viscosity force between each layer to each layer, which is parallel to for example, this plane, which is going to make a shear, and it will make also a shear between the top layer and the wall. Okay. So when we are saying it is a rigid body, that means the fluid itself is not moving internally, so there's no swirls here, there's nothing. It is a rigid body. Imagine it as it is in a container, and acceleration, which is mean it is an static point, but the entire body is moving as a rigid. You get my point? So there is no any viscous viscosity effect on the wall, between the wall and the body of the water or whatever, and between the water and the water itself, because it is a rigid body, or it is in a confined space. Okay, so it is like a tanker of water moving within acceleration or decelerate or something. Okay, we are going to apply the same concept: pressure, 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 pressure. But and here, from the point here in the middle, in the center, there is a weight, yes, and plus there is an acceleration. This is which an addition, because we know the acceleration, assuming, so the acceleration from the center of the body, it is just the same. But for example, when we said here it is delta Vy is equal to 0, no, it is equal rho dx dy dz, the volume multiplied by the acceleration in x direction, and acceleration in y direction, and acceleration in z direction. So we write it like this, which is dx dy dz will go by dxy dz, as we discussed before, and the same and the same. But here, just remember that it is not only acceleration in z direction, because acceleration in z direction is equal to the acceleration in z direction minus the acceleration of the gravity of acceleration. Of course, minus because this is opposite way, and vectorial, of course. Okay, so it is very simple, so we can write it like this in this term, and it is very important to understand it. So if we are going to say that is this pressure is equal to this one in x direction with minus, and this one is equal to this one with minus, and this one with this equal minus, we can put it together in one equation, but we need to identify x and y and z by writing the first axis I, G, K. So of course the minus can go here, it is not a big deal. Okay, so rho G minus rho A factorial, or with so with vectors, with respect to vectors, is equal to the rate of change in x in the I axis, which is x axis, and the rate of change in y in J axis, which is the y axis, and K, you know, like when you're flipping the axis, we are writing I, which is square root of -1. And it is the same, but in another axis, and it is the same in another axis. But it is just a symbol to identify these different axes. But why we need to write it like this? Because this form, we name it is a Laplace operator, or the gradient. The Laplace operator is the rate of change of a function in respect, or the partial change of the function in respect to each axis, in respect whatever any axis you have. You have three axes on each three axes. So we can write the plus operator, or the gradient, of course, with a vector, which is we have x, y, and z of the pressure. So the gradient of the pressure is the rate of change of the partial derivative of the pressure in respect to x plus the partial derivative in respect to y. And you can break this one in three equations. Okay, so it is just to make it simple writing. Okay, and of course we can keep this one here and shift this one here, whatever it is. Just rigid body rotation. Rigid body rotation also is very simple, very easy, same concept. We have a body rotate, so the water is rotate still because it is a rigid body. So the entire body is rotate. It's not meaning the top body is the top layer is rotating and the lower layer is not rotating. The entire body is rotated in the same body. Imagine it like you have a blender, and the full of the water is moving or rotating as a full body. Okay, so we take a small slice, same 3D slice. We will take z direction. This is assume it as x, but we will name it r. for simplicity later on to write the numbers. And imagine here in something named z direction, but we don't have it. Why we're saying don't have it? Because if you have a circle and this in the direction, etc., it is symmetry. We assume it is a cylindrical vessel, so it is symmetry. So we can assume we don't have, sorry, in y direction. We don't have it because it is symmetry. Okay, so we are going to use between z and r. Due to the rotation, we know that the acceleration, the centrifuge acceleration, or because there will be a centrifuge force, and the force is acting as a mass multiplied by the acceleration. It is r omega square. Omega is the radial velocity, or it will be Vr multiplied by r. But we're going to use this one. Okay. We know that this surface is equal pressure because it is to the atmosphere, and parallel. Each surface is an equal pressure. Okay. Just this one we'll know it later. Okay. So we know that as we have a g, and we have an acceleration a, still in general form. We didn't still say what is the a direction and what is g direction. It is vector g, vector a. Vector g minus vector a, gradient or plus operator of p is equal to, يعني this one is an equation itself, which is equal to grand g, or the total g, which is between a and g. Okay. Of course, here is the acceleration in this direction. So minus a, it is in opposite direction. So full g, it will be in this direction. Okay. Okay. Write the same equation. What we have, dv, or del b minus del b by del x equal rho g. Okay, gx. Okay, g is the total acceleration. We know in x direction, which is as we agree, so yeah, I assume this one is y and this one is x. We know because it's symmetric, so there is no acceleration in x direction. Okay, so is equal 0. So we can neglect all of this term. So in z direction, which is vertically, no, we know that there is acceleration g. We know that there is an acceleration downward, and there is an for gravity, and there is an acceleration in r direction. Okay, so minus z, which is equal only gz. Okay, and in r direction, which is equal only this one, which is r w square. Okay, omega square. So there is something here we need to understand it, but we're going to open it later on. If I need to know, this is a partial derivative. If I need to know the full derivative, not the partial derivative, the full derivative of a function, it is equal to the partial derivative of that function in respect to the first parameter multiplied by the full, multiplied by that function, or the derivative of that function, of that parameter, plus the partial derivative of pressure in respect to r multiplied by dr. This is the rule if I need to know what is the total change in the pressure by logic. If the pressure is going to increase in z direction with 1, and it's going to increase, or the rate of change in the pressure in z direction 1 per each 1z, and the rate of change in pressure in r direction is 2 each 1r. So what is the length of r multiplied by the rate of change of r due to r, and what is the length of z multiplied by the rate of change of the pressure due to z, added together, it is dB. This is logic. It is not an equation which is you need to derive it. This is a logic. Okay, so dB is equal to this one dz, this one dr. Very simple, very straightforward. Okay, so this is a total change in the pressure. So we know this, so we can integrate the full. We know that there's nothing here, so it is dB equal to b. We know that rho g is constant, so integration of dz with nothing, with constant, is z. We know that here if I need to make an integration, no, I have r. So integration of r dr, it is r squared over 2. So it is rho omega r squared over 2. Sorry, this one, there is a square which has been missed. However, it is written back again here. Okay, this is rho omega square r square over 2. This is the pressure. Okay, very simple, very straightforward. If I want to know what is the h when this rotate from this point to this point, how much the rise of the water, it is very simple. So divided by rho g, divide the full term by rho g, so it become h, which is equal to, we know at h, here is pressure is equal 0 to atmosphere, so pressure equals 0, equal to this term, z is h, put it another way, so divide by rho g, omega square r square over 2 g. Okay. Now we'll go to the continuity equation. Continuity equation, it is also we're going to say use the same philosophy. We have a slice, but here there's no pressure. Here I know there's a mass flow rate in this direction, or we assume there's mass flow rate in this direction, coming in from here, coming out from here, coming in from here, coming out from here, in here, out here. We need to understand that there is no change in the mass here, which is mean whatever get in must equal whatever get out. So sigma mass in should equal to sigma mass out. Okay. So for our simplicity, in for example this x, this y, z, whatever, forget the direction, you can flip it the direction, but any velocity in x we name it u, any velocity in y we name it v, any velocity in z we name it w. Okay, and we know that the mass flow rate, or the rate of mass flow rate, is equal to the mass itself, it is rho g volume. The mass flow rate, it is rho g volume multiplied by the velocity. Remember, q equal velocity multiplied by the area, if you remember this point. And the mass flow rate is equal to density multiplied by the area multiplied, etc. If you remember from the fluid, but it is way very simple. Okay. You think so? There's no g here by mistake. There's no g. There's no g here. Okay. So let's put it in the same concept. For example, I have an x. I have n. N should be in positive. Okay. Or whatever. And let's don't say it like this in or out. This opposite direction of x. This opposite direction of x. But this as in, this as out. Okay. So I'm speaking about u, so forget this minus now, forget it for now. Okay, so truncated Taylor series, same concept. I have this point, I need to check it, or I need to check this point, which is in the x. So this I will refer to this in increasing of x, so it is rho u multiplied by dz dy. It is the area, rho velocity. This is the mass flow rate. So this equation is incorrect. Plus the rate of change, because I am referring it in the increase of x by the distance, okay, which is dx by 2. Okay, and this one, forget also the plus and the minus, we're going to discuss it later. Okay, same, I have a 1 point here, u in this direction. Okay, I needed to refer to this direction in opposite of x, so it will be rho u here minus del rho u by del x in the distance, dz dy, dz dy, the area. Okay. Now, I know in this one in opposite direction of x, and it is in mass inflow. So mass inflow is positive, and it is in opposite direction of x, so it is negative. Positive multiply negative is negative. Okay. Here, mass flow, it is out in negative, and it is in the opposite direction of x, so it is in negative also. Negative by negative is positive. So this is how we get negative and positive. Repeat the same here, here. So in y, in z. Copy paste is the same. Then you write all of together should be equal 0, or we name it in another way is the rate of change of the body itself without knowing if there is any velocity. So the rate of change of the body itself without knowing the velocity, the rate of change of the time. So if I assume this one is 1 kilogram, the rate of change in this control volume, for example, if there's no any velocity, only there is velocity here, which is giving 1 kilogram per second, 1 kilogram per second. So I know that is the mass of this slice will increase 1 kilogram per second because the volume is fixed. So, and the mass is equal rho by v, volume is fixed. So the density going to be increased in respect of time without knowing any velocity. Okay, so the concept of the rate of change in the density multiplied by d volume, which is dy dz dx dy dz by time in a control volume, should equal to sigma mass in minus mass out. Okay, put it all together. It is not, there is no any vectors. If you can see, there's no any vectors, so we can put it in one equation without ig. Okay, whatever. So, but we know that is the density, we assume it is incompressible. Let's just assume it incompressible for now, or if we keep it يعني, if we assume it is if it is compressible, so keep it under the del. If we assume it is incompressible, so we can put it outside. Okay, so the rate of change in respect to z, the rate of change in respect to x, the rate of change of the velocity of respect to v. I just added this together. So of course, you will find this will go by this one, algebra. You will find this equation, which is equal to the rate of change of density by time. What is this shape? This shape is a gradient, but take care that this shape is a gradient, not for a constant rho. Yes, it is for a vector velocity. So the velocity is a vector. When the velocity is a vector, so we need to write a vector. Later on, we understand why we need to write a vector. So gradient vector or a Laplace operator for a vector, which is me, when you're going to x, you need to select x, the velocity in the x direction. When you are checking the change of velocity in y direction, you need to use only which is in y direction. That's why in z w, in x we write it u, in v we write it so in x y, and this y is v. I will correct this one as y. Okay. If it is incompressible flow, you can put the rho outside, so rho by rho by rho by rho by by all the rows. So we know that the rho will not change if the concept is the rho is constant, which is mean whatever in is whatever out. Sigma is 0. So the control volume cannot absorb a mass, which is this one is equal 0. So this one, this one, this one by. So it will be du by dx, dv by dy, dw by dz equal 0, which is the gradient or the plus operator of a vector v equals 0. This is the derivative for Cartesian coordinate, which is x and y and z. You can assume or you can take the derivative for the derivation for it in cylinder coordinates. Cylinder coordinate, it is very simple. If you have x, I will just do it, for example, if I have a 2D, but you can know it later on. If this one is x and this one is y, this is an x or Cartesian coordinates. If you want to do it in cylindrical coordinates, it will be easier for us for something later on. So we have a one direction r, and one rotated direction is theta. Of course, if you have z, z will be the same. So either r theta z, this is cylindrical coordinates, which is mean and this is Z, and this is R, and in this direction is theta. Why we need it? Later on it will be easier for us in case if we have cylindrical shape, it will be easier for us. So how we're going to reach this one? Just apply is R is equal x square plus y square, and theta is equal to tan inverse y over x. If you use these two equation here, whatever the derivation, you will reach to here, okay, which is 1 over r del r u r velocity in r direction by del r, etc., 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 till you will find. Okay, now the material derivative. Before to go in the material derivative, we need to understand something. In case of a steady, no change in the time, which is mean we said it is steady state. If I said it is steady state, for example here, you will tell me there's no change in the time. For example, if I told you here is steady state, or there is a rigid acceleration here with a steady state, or there is a flow with a steady state. Steady state, that is means there's no change in the time. When you tell me there's no change in the time, you will find somebody who say, okay, there's no change in the time, which is mean no change in the velocities, because velocity is the function of time, or it is distance over time. No. A steady state means that is there is no change in respect of time, but for uh, a certain streamlines. For example, that is mean the streamlines is not going to change, but the velocity itself, it can be increased, but it will not be increased in the same point. For example, steady state, that is mean this point velocity is fixed, it is steady, it is not changing, but it is different than this one. Because it's different than this one, because for example this converging duct or pipe, so the velocity should be increased. So it is steady yet, but the velocity between this one and this one is different, which is accelerated, which is means the acceleration is change. So now we understand that is steady state is not meaning that the velocity is not changing along of the pipe or along of the flow, and it's not meaning there is no any acceleration. There is an acceleration. Okay. By another way, acceleration mean forces. Okay. Type. And we understand before, as we discussed, that is acceleration is a body force, like gravity, acceleration of gravity, or an acceleration of, it is a body force. Body force, it means it is acting on the center of the body. Good, good. So if I have something accelerated at the center of the body itself, but remember that I told you it is crucial to know what is the acceleration, for example, for rotating. We need to know what is acceleration, because acceleration acting on the body. And when we discussed here, I told you we know the acceleration. Tank is moving in with an acceleration, so we know how much is acceleration. Imagine if we don't know the acceleration, and the acceleration is due to changes of the velocities, like here. So we don't know exactly how much is the acceleration. We know the velocity change, how much. Okay, this is very simple. We can say this one minus this one over the time, so we get the acceleration. Yeah, but this will never be the case very simple like this. So if I need to know something which is acting as a body force or a body entity, and I know that is a velocity, it is not a body entity, it is a field, which is mean there is velocity here, this velocity, this velocity, 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 and it is a field of velocities. In another way, Lagrangian perspective, it is acting as a particles. So it studies the particle, the center of the particle or the particle itself. For the velocity fields, it is from Euler, Eulerlian perspective, which is a field. To make a relation between something acting on a body, or a body force, or a body entity, or a particle, to a field, we need to make something the material derivative or the chain rule. Chain rule is very simple. We already discussed it before, and we're going to repeat it again. We discussed it, but maybe it is written back here. See, the total change on something is whatever partial change of something multiplies the something. The logic, what we are using it. We're using, but in a deeper dive. See, so we know by any case that the acceleration or whatever is the velocity is it changing because of the time, a parameter. So this is a parameter, and we know it is changing in respect to x. So it is changing respect to time, changing respect to x, changing respect to y, changing respect to z. This we all know it. So we know that is dv by vector, whatever by dt by del t, and we have del v by del x, del v by del y, del v by del z. We know all of this. Okay. We need to know, we need to know, or we need to get the derivative of this one, right? The material, the total derivative, the material, we name it material derivative. So it is very simple. It's not simple, but so we need to check what is the distance, as we discussed it before. But it's we are not dealing now with the distance. We are dealing with respect to acceleration, right? So, oh, so irrespective of velocity. So we need to check the dx by dt, dy by dt, dz by dt. Again, dv by dt, or del v by del t, this is the partial. At the end, I need to reach to, at the end, I need to reach to the acceleration, okay? Or the change in their time in respect to the first axis, which is dt, here, like before. So del b by del z multiplied by dz, same. So it is del v by dt multiplied by dt, del v by dx multiplied by dx, del v by dy, del v by dy, by dy by dz. Till here, up term is, we know it. Okay? But we are not trying to get the velocity, we are trying to get the acceleration. We know that is the acceleration, it is the velocity by dt. So it is dt, 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 dt. Okay? Because we're trying for the acceleration itself. Okay? So dt by dt is 1, dx by dt is u, dy by dt is v, dz by dt is w, which is the velocity in all direction. Which is we can write it like this. How we write it like this is dv by dx, or which is mean in x direction because vector, so it is del u by dx by del x, del v by del y, del w by del z. It is a gradient. So it is the gradient of the velocity. But remember, gradient of the velocity multiplied by the velocity vector, which is mean u, v, and w. Now concentrate. Gradient of v, the gradient rule of v, which is mean in if it is in x, so we are going to use u. If it is in y, we're going to use v. If it is in z direction, I'm going to use w. Here is no gradient. Here is no gradient. It is the vector itself. So we are going to multiply the vector. So the vector component is what? The vector component is u, v, and w. The three of them. So if you're going to write it in x direction, of course this is by dt, del v by del t, so del v by del t, equal to, or plus, du by dx, gradient, dv by dy, gradient, del v by del z, the gradient. Oh, sorry, del u by del x, del u by del y, del u by del z, the change of u in each direction, multiply by this in x, so in u, this is in y, so it's in v, this is z, so in w. If you remember here, yes. So the change of the parameter in x, the change of the same parameter in y, the same change in z. This is a gradient. Okay. So when we are dealing in x, as we discussed, we are dealing in x, so we're going to use u. If you're dealing in y, we're going to use v. If you're dealing in z, we're going to use w. Straightforward. But because this one is vector, it's no in respect. So because here is x, u, so it's the same direction. Here y is v, here z is w. Okay. Same applied for y and z. What is this? It is equal to what? We need to get what? dv by dt. Oh, the total derivative of v by the total derivative of t, which is the acceleration. So we can remove the acceleration term here, and we can write the lengthy derivation what we are done. So of course this one in xy coordinates and this one in cylindrical coordinates. Same concept we discussed before. What is cylindrical coordinates? So if we're going to go to the Navier-Stokes equation, Navier-Stokes equation, we just added the viscous force. The viscous force itself, it is rate of change or the gradient for the second time, or for the power of 2 to the velocity, because the velocity itself or the force itself, it is the rate of change of the velocity by the distance. So the rate of change of that force is the second derivative. It is long derivation with matrices and etc. But you can imagine it like this. If you go onto textbooks to check how is the derivation of this term itself, because Navier-Stokes is taking this term, Euler equation is the same Navier-Stokes without this term. Okay. So this one we can put it like this in x direction. This one is the same. This one is the same. So it's the second del square, because the second derivative by del x, del u by del, because in x plus g in x, y, and this is in cylindrical coordinates.